then start sharing my tablet, and we'll see how that goes. Should be fine. I have done that before many times, so let's see. Okay, do you see anything, or I'm just going to scribble?
Yes, that's visible.
That is visible. Good. That's important. Like, this is not important what I scribble, but as long as it works. So let's begin then, right? So what we did last time is that we started with an abstract coarse structure. Oh, I think I wrote on my scribbling. I don't even notice that. Right. So we started with an is it still visible this far up, or is it not visible when I go that far up?
Right now, the tips of the letters are not visible anymore. Yeah,
because they go under these green buttons.
Okay. Now it's perfectly visible.
Yeah. Okay. So I don't know. I know how much up I can write. So last time we started with doing an abstract version of it. So we said, okay, we will generalize just for fun from how we had defined the large scale geometry for metric spaces and see what we get out of it. But last time I did not tell you what one of the important goals of this exercise is, right? So what we learned, and I will repeat this again. So again, just a review, but for now, let's just say that we learned that if we have a compactification, so if X is paracompact, locally compact Hausdorff space, which is every metric space, every group that you would ever be interested in, right? Then any compactification of X gives rise to a large scale structure or coarse structure. Okay, so this is something we did last time. I will repeat this. No worries about it. But what's such a big deal about it? So actually, even if you're only interested in metric spaces, which many of you are, I think, are coming from the metric geometry world, there is an amazing theorem. There is an interesting theorem that I wanted to cover. So this is kind of our goal today, which maybe like always might be dragged on to the next class so that we can review it again. But the goal is that there is a compactification. So if X P is a proper metric space, then the large scale geometry of XT is the same as a large scale geometry of a certain compactification. Okay, I will explain what this compactification is. That's a part of our goal, right? We don't know what it is now, but this is our goal today, right? So even if you're interested in large scale metric geometry, what turns out to be that you have this compactification, and you could sometimes obtain your results about your metric geometry by studying compactification, by studying this compactification or its quotients. Okay, so this is why this abstract formulation is powerful. That it's not just giving you new examples, it actually lets you see your good old example in a new light. Do you see what I'm saying? So it's not just abstraction for the fun, but it also gives you some new tools. So we will not do much about this new tool in our course because that goes very much into specialization. And that's not the part of plan for the course. The plan is to more or less say, we will basically get to this point that we know that even our metric large scale geometry can be studied using compactifications, right? So let me go through the revision of the compactification. So this is our goal. I'm going to move it a little bit up. And I'm going to, for myself, draw a line here. So just a reminder from last time. So what did we say is a coarse structure? So on a set X, a coarse structure is what? It's collection E, a collection of subsets of X cross X, right? And this E behaves like the scales. So this should behave like the scales. So should behave like scales for metric spaces. So we wrote down all the axioms, an axiomatic version of it, that the diagonal is certainly in E, and subsets of something are in E, and products are in E, and inverses are in E, and unions are in E, and so on. So that is what, so I will just write maybe if E belongs to E and F belongs to E, then E composed with F, E times F. Oh, sorry, that's the same thing. These are two notations for same thing, actually. E union F and subsets of E are in E. Okay, so that, am I forgetting something? Maybe I forgot something. I don't want to be too careful when I'm doing a review. Reviews can be slightly, what do you call it? Inaccurate, okay? But this is more or less, you get it. So this behaves, so this composition is where we get the triangle inequality, right? So you have to remember why we put such a condition. And I think another thing which I forgot is inverse belongs to, okay? And this is, but what we also saw is that so far we have defined this only for a set to have a compatibility, with a topology on X. So now instead just saying it's a set X. So suppose X is paracompact and locally compact Hausdorff. LCH is locally compact Hausdorff. As soon as you write locally compact Hausdorff, you can use your theorem of converting this space into the space of continuous functions, right? So that is another advantage of it. So suppose that X is this thing, then a coarse structure is proper. Structure that's some collection of subsets of the powered set of X plus X is proper if this collection contains, so there is so by the way, these elements of this collection, I should remind you again, are called controlled set. So there is a controlled neighborhood of the diagonal. So there is a control set, which is a neighborhood of the diagonal. It should not, so it connects this one particular control set to the topology. And we define something called bounded subsets of the coarse thing. So every bounded subset that is B in B subset of X such that B cross B belongs to E. Every bounded subset is relatively compact. So if something is small in your large scale geometry, it should also be small in your topology. That is what this means. So we said that we need to put in these two compatibility conditions to join topology and large scale geometry, right? So I'm going to repeat things just so that you don't have to always look up your notes. And then there was the fascinating thing, right? So this is the abstract definition. This is the abstract requirement of compatibility. And then something happens. And actually, we did not prove this last time completely. So we said that if X is everything, so I might start writing it PLCH, paracompact and locally compact Hausdorff. Sounds like too many properties, but almost anything you know has these properties, right? So don't worry about that too much. So if X is locally compact and paracompact space, then, and this is a compactification, then it defines a coarse structure on X. And so that was a set E is controlled by the compactification. A set is controlled by compactification if you have any net. So now I am writing net because I was assuming last time second countability or something, but let's just write. I suppose you have done your analysis courses, right? So if this is a net, in E such that X lambda converges to the boundary, right? So X lambda converges to X in boundary, and Y lambda converges to Y, to anything, then Y equals X. Okay, so this is your condition on a set being controlled. A set is controlled if, so this looks like very tedious condition a priori, and I will explain it again. I explained it last time, but what it is saying is that a set is controlled if it has points going to infinity. If it has points going to infinity and converging somewhere, then they better converge to the same X and Y coordinate. Right? So if you have a subset of X cross Y, and you can have sequences converging unboundedly, then if they converge somewhere, then both X and Y components of these sequences have to be the same. That is the only requirement. A fancy way to put this, so this is
sorry,
equivalent.
Could I ask you to repeat the such that part? I didn't hear it right, and now I can't read it.
So which is the given and which is the implied. So you have a net in which both the components converge and one of them converges to the boundary. So this is given to you. So X lambda converges to X, Y lambda converges to Y, and X is on the boundary. As soon as one of the points converging is on the boundary, the other point must be the same.
Okay, I got it now. Thank you.
Okay. So another way, so when I reformulate it, you will see that. Another way is that you take the closure of E, closure in X cross X. So take the closure in the compactified thing. So all the points of this which are not in X cross X. So if I take away all the things that are not in X cross X, so if I take all the points in X cross X out, then this should be contained in the diagonal of the boundary. So this should be contained in delta X cross delta X. Okay, so usually the boundary of this whole thing is X cross delta X union delta X cross X. So this is what you have at infinity, right? So if I take let me make an example. So if my example is the interval 0, 1, so x is the 0, 1, x bar is close 0, 1, right? So when I take the product x bar cross x bar is the closed square. And the points on the diagonal are just these 2 points. These are the only points on the diagonal. The other parts of the square are not on the diagonal. Right? So this is a condition that it says that you're not going to, and such conditions are very common in analysis, by the way. This is just a fancy way of writing boundary value problems. If you ever study them, they're full of conditions which you can reformulate in this language. So that is also why this is an interesting field in itself. Okay, so if I have managed to confuse you, that's very good. I think the explanation is again in the notes, but this is the definition of what it means to be that a set is controlled at infinity. A set is controlled by this compactification. So this is what it means. So as of now, it looks very abstract, right? And the theorem is that, I don't know how I stated it last time, and I don't know how it's stated in the notes, but the theorem in some ways should be the following. So we have, let X be a paracompact, locally compact Hausdorff space, and X bar a compactification. Then collection E equals all E controlled by X bar is a proper coarse structure. So remember, this is then not just a coarse structure by itself. It's not just a collection of subsets of X cross X. It is a collection of subsets which has the required compatibility to the topology of X. Right? So we need to show that it has the required compatibility to as well. This is a necessary. Oh, I think I forgot. There are three conditions. I only mentioned 2 of the conditions. The third condition I will remind you when I kind of prove this theorem. So this is the magic of starting with compactification. And how do we get compactifications? What are compactifications? In a functional analytic version, a compactification is very easy to describe. So compactification comes from subalgebras of bounded functions on your space. Right? So we will see that we use this quite many times. Is this clear so far? It's a little bit abstract, but it's we'll get to being more concrete in a bit. So before I do that, let's look at the obvious compactifications. So we have a locally compact space. So one obvious compactification, so just an example. So if X bar is X union infinity, is the 1-point compactification, right? Then what sets are controlled in 1-point compactification. So if you want to think about this definition of controlled set, you should think about it for a minute or whatever. That's why, it's kind of missing in a classroom. I would just say you should discuss with each other. But how can I ask you to discuss what you mean by something on internet? Maybe you can chat. What do you think are controlled sets of X union infinity? That's a way to see if you have thought about the definition, right? Okay, I give you half a minute. People like me have to learn to teach online. I have to say, it's a little bit difficult. Any ideas? When is a set controlled at infinity? There is only one point at infinity. So if something goes to infinity, what is guaranteed? It cannot go to two different places, right? So one part of your problem is well controlled by this special event that there is only one point at infinity. So in this case, E consists of all proper subsets of X plus X. And by proper, you mean that sets on which both the projections are proper. That's it. Right? Because if anything converges to a point at infinity and the thing is proper, then the other component has to be infinite. But if anything is infinite in a one-point compactification, then it must converge to infinity. So there is no issue here. Okay, so this is this kind of the most simple example. So this is what we defined last time. It's called indiscrete coarse structure, and it corresponds to the one-point compactification. Right? So this is one example of an abstract coarse structure. Going on, let's just look at the proof for at least some part of the proof. The interesting part of the proof. There is some part which is just what you call it. If you think about it, it takes 1 second to do some steps. And if you think about it, it takes a lot of time to do some other steps. So that I'm going to do the steps that are really hard to do. Okay, so I think it's very easy to check that everything, composition, whatever you want of such sets is again such a set. So the part that E is closed under all required operations is pretty much set theoretic. Like you do set theories, X belongs to this and Y belongs to that, then X belongs to Y, blah, blah, blah. It's very, very much operation dependent. If you're not confident, please try this out. So E is closed under all the operations you need. So that is no problem. That's easy. But what we want, we have claimed more. We have said that it is compatible with the topology. So we need an open neighborhood of the diagonal. Okay. So now we have X bar cross X bar. And we define two functions on X bar cross X bar to 0, 1. And to define these two functions, I'm going to define two subsets of that. One subset is the diagonal, and the other subset is the boundary. Okay, so one subset, I'm going to take the diagonal. Set 1 is the diagonal. And set 2 is the boundary of. So boundary X times X union X times delta X, something like that. Okay, and now I can apply a famous theorem, something called the, how can I get functions? How can I get open sets? Open sets are inverse images of open set. So if I can get continuous function from here to the open to the interval 0, 1, then inverse image of something will be an open set, right? So this is the whole trick. This is how you make open sets. So you need to have functions. And if I give you two sets on something like that, how would you make functions? What is the first thing that comes to your mind? Shall I write it? Actually, am I readable when I write? Something like that. Can you read it?
Yeah, I mean, with the context for sure.
Okay, at least with the context, right? So I'm talking about two sets, and I have assumed paracompact and locally compact Hausdorff, which is true for all your metric spaces generally, well, not for Hilbert spaces. So you have Urijons's lemma. This is why I have assumed these properties. Otherwise, I did not need to assume these properties, because I need to use a theorem like that to produce such functions. So I will produce a function which is 0. So I can obviously have a function f, which is 0 only on the boundary. So I just call it delta of x bar across x bar. And g, which is only 0 on diagonal, right? Given a closed subset, you can find a function which is only vanishing on that closed subset. Good. Now I can define my set E to be all xy such that gxy is less than fxy. So this thing is certainly an open set, right? And it contains the diagonal. So diagonal is contained in E, and E is open. Because on the diagonal, what do we have? On the diagonal, G is certainly bigger than 0, and F is 0. Oh, sorry, G is 0 and F is not 0. So diagonal is in this set, and by virtue of how we define this set, it's an open subset. So this is actually why we have been using this topological machinery to define such structure, right? We need paracompactness exactly here. So if you see anywhere else, you would not need this. I mean, you need this because you will use this facts over and over. But in the deepest level, this is where you needed paracompactness. Okay. All right. So that proves one thing. I think I'm going to. Is there anything else I want to talk about this? I will write some more details about the proof, but I think this is the crux. This is the only difficult part. Everything else is manual, right? So let's not worry about the manual parts. Let's just focus about hard part and examples and understanding what's happening. So what we have now, that if we have a compactification, so let me rewrite, say, so if X is a compactification of whatever paracompact locally compact Hausdorff space X, then it gives us a coarse structure. Okay, so this is the whole point of thinking like this. Yeah, so far so good. Why are we interested in this? We are interested in this for two reasons. One, I have mentioned as our goal for the lecture today. And the other is a theorem that I will write down, and that will explain some regularity to you. So if f from X to Y is a proper continuous map, Okay. This is given, then F extends to some compactifications continuously if and only if F is a coarse map for the coarse structure corresponding to X bar and Y. Okay, so it makes perfect sense. Sometimes you need to extend functions continuously to the boundaries. And usually it's hard to understand when a function extends continuously to some compactification to some boundary. It's a difficult problem. And here is one possible way to look at this extension problem. One way to look at this extension problem is through this coarse structure. So you can look at the sets controlled by E, the sets controlled by your first compactification, and the sets controlled by the second compactification, and you can just check if these control sets are mapped to control sets. And that way you know the continuity of the extension. This is a difficult problem usually, right? So this is one reason why the compactification is anyhow interesting when you want to extend continuous maps to the boundary. Okay, so I will maybe try and describe the proof of this a little bit, but I think it's not so hard to see why you want such a theorem. You want such a theorem because not just as, even if you're not interested in large scale geometry, you are often interested in extending a continuous map to the boundary. This is why this theorem is interesting beyond large scale geometry, right? Okay, so do you have any questions so far? All right, so maybe this was not my plan, but this online makes things more kind of a theorem proof example kind of a business, but I don't know how to do this thing otherwise, because you cannot interact and jump around in an online lecture. Right? So you cannot talk about Dostoevsky in online lecture, can we? Maybe. I will tell you why I mentioned a particular author and not anybody else. It has some relation to large scale geometry. Anyways, so what do we want? So we want to say, assume that F is continuous. So assume F extends continuously from the compactification to that compactification. Okay, from one compactification of X to a particular compactification of Y. I don't care what these are. And my claim is that this is a large scale map. So properness I have already assumed, right? So that takes care of it. So let E in X plus X be controlled by X bar. What does that mean? We will see this again. And our claim would be that we need to prove that F, I don't know, usually people times F cross X of E is controlled by the other compactification, right? So this will prove one way of our statement if we show that. And how do we show that? So we take sequences X lambda F Y lambda Okay, so this is sequence in the image. So this is in y plus y, such that fx lambda converges to say y in y. Okay, so maybe y1. I need my magnifying glass. And our requirement is that if we want to show that this set is controlled, we need to have this situation. In delta. So we need to be in this situation that both the components are converging and one of them is converging on the boundary. And to say that the set is controlled would require us to say that these two guys are the same. Right? But we are given something. We are given that f is continuous, and from this we can get this. Okay, so this is a little bit of a hard work in some ways, but it's straightforward. Don't worry about how this goes. So if you have a net in a compact set, you can find a converging subnet, right? It does not matter how. So you can say, without loss of generality, I can assume that x lambda is converging to some x by going to a subnet. Right? So if x lambda converges to x and f is continuous, since f is continuous, it means f of x equals y1. So maybe I should call this x1. Sorry. Okay, so if this thing is in that, but since y1 is on the boundary and f is a proper map, what can you say about x1? What can you say for sure about x1? If you have a point at the, if you have something whose image is at infinity under a proper map, then the original sequence should also be infinite, right? Otherwise, you will not have properness. Otherwise, you will have non-properness. So this implies that x belongs to delta x. Sorry, x1 belongs to delta x. This is as f is a proper map. So maybe I will explain these things again, or you can think about this by yourself. Usually these things are good for discussions why such things happen. I don't like to explain everything too much. Oh, I will have all these notifications. I forgot about that. Okay, you will have to live with a few notifications. Anyway, so we have one condition that this is on the boundary. And we can also similarly say y lambda converges to some x2, right, by going to subnet. But now E was controlled by the compactification x bar. That implies that x1 should be equal to x2. Okay. And once you have this condition, what does it imply by continuity? By continuity, y1 is f of x1 equals f of x2 equals y2. And of course, it then belongs to the boundary. And you're done. Okay. So although you might think this is crazy, but looking at these kind of subsets and how a function acts on these subsets converts continuity into large scale structure, and vice versa. The argument is pretty much the same. It's not, I will do it, but it's not terribly far away. One should do it a few times to get the hang of it. Because usually one is only talking about topology. One is only talking about things that are local. And now we are talking about things that are going to infinity and combining them together. So that is the sort of crazy part of this. So conversely, I don't know if the C got it. What happens? Oh, I am writing beyond the edge. Sorry. Have I been doing that? Only realize now that I'm writing beyond the edge. Then I wrote this conversely. Conversely, let's say F is a coarse map. Coarse map from x to y. How can you show that it's continuous? So we have to show that if I have a net x lambda converges to x in x. I have a net that converges to a point in the compactification, and I will just define the following. I will just say define the value of f. So this is my extension, the value of f at x to be any accumulation point of f of x lambda. Any. So this is my definition of the extension. But is this good enough? What wrong I am doing if I say this is the definition of extension? Come on. Somebody
you need to check it's well defined, and that's going to use
well defined
coarseness.
Is it well defined? Right. So we need to have another sequence. So we need to have another net converging to x, some other net, and we want to see that this will be the same thing. But remember what we have. So we have that f is proper, and so what we get is, what did I say? Oh, I selected something. Okay. Oh, I'm getting very warm here. Let me just, oh, wait. Just wait. My office is too hot. I came from outside wearing all of this stuff. It feels extremely hot here. All of a sudden, this is unbearable. Okay. So we have to show that this is well defined. So where did I write? So f is proper. So what I want to say is that f of x lambda. I kind of think I'm forgetting something. I see. I see. I should have said something else too. How do I do that? Maybe I'm just going to move on a little bit and then write it again. So I forgot to say something in trying to explain this part. What I want is this to be well defined. So what I have to do is start with functions. But let's just try to see if I can do it like that too. You should usually start with functions. So I want to say that in the limit, this is equal to that. Fx lambda prime. Right. So you want both these things to have same limit, and why should that happen? Okay. So I take a continuous function phi on y bar or on x bar. Yeah. Okay. And I compose it with f. So this will now be a continuous function on x. So this is a continuous function on x.
So you're composing phi after f, right?
Yeah, so I do mean phi after f. That's true. Somehow I'm getting confused. This is a very simple argument, and I don't know what has happened to my brain all of a sudden. This is a very simple argument. I have, in some ways, I get confused sometimes. But I don't want to, as you know, it would take me forever to look into the notes. So what I want, the first thing is that this is well defined, and it's well defined because these two limits should be the same because f is proper. What you have to always remember is properness means that outside the so inverse image of compact sets are compact sets. So as one thing goes outside a compact set, both the sequences are going outside compact sets. So the difference between the two limits should converge. This is the whole point of this exercise. So I want to not write down the detail of it, but this is saying since f is proper, you can choose by taking inverse images of compact set by taking inverse images of compact sets in Y, make the difference between fx lambda and x lambda prime small. This is the idea. So you can remove more and more elements of your net. So what is left is converging. It will be a convergent subsequence. So you want to say that the limits are the same. But for some reason, I don't see it right now. But the idea is you have to be able to use properness. That's the only thing. Okay. So rather than wasting all our time, I will anyhow include it it's included in the notes, so that's not a problem. But this part is actually important. I wanted to do it carefully, and I forgot. I'm sorry about that. So let me let me say what I'm saying. So we have proved one part of the statement, and the other part is the most interesting part because we want to use that part, right? We want to use, where did my statement go? We want to use this theorem. Where did I write the theorem? Cannot even find the theorem. Oh yeah, here is the theorem. So we want to use this theorem, and to be able to use this theorem, I want to prove this properly. And one part we have proved, but that's not the part that we use. That's the part that you will use if you ever want to extend a function to the boundary. And this is why this theorem is actually useful, right? But the part that we want to use is that given a proper map, which is a large scale map, it is automatically continuous. And it is automatically continuous because you define the value at a point at infinity by taking some limit, taking some sequence or some net converging to that point, take the image, and that's the value of the function. This value has to be well defined. This is what I'm unable to check. So I'm also unable to check why it is continuous, right? But this is the part we will use. Unfortunately, that is the truth of it. The second part, sorry?
Can't you just define set E by x lambda comma x lambda prime, which will be controlled, so f of it will also be controlled?
Thank you. I think that is the point. So you are paying attention, my friend. Thank you. So I have to define some sort of a code set in which you can define something like that. So x lambda prime, but this is not, this can have, as long as they are both converging to the same point at infinity, this is certainly not necessarily a controlled set. I'm not given this fact, but I want to have this contained in a controlled set. So I can always say that there is a controlled set containing this sequence. And that is the point.
But they both converge to the same point x.
But I have never assumed that a singleton, for example, is a controlled set. So I've just not said that like x comma y is a controlled set, right? But yeah, they both converge to the same point. But that's good enough, I think, right? What else do I need in the controlled case? So let's just check. All right. So you're right. So this is a controlled set. I take it back. So our requirement for controlled set is the following, that whenever there is a sequence converging to infinity, both the points should converge to the same thing. So E is a controlled set, and then f of E should also be a controlled set. Right? So what we have said is that f of x lambda, this is how we define the value. So we define f of x equals f of x lambda equals y, but this should also be, since it's controlled, should also be f of x lambda prime. Wow, you are paying good attention. This is really not even about properness. We really have gotten that this map is well defined just by using the fact that E, which is x lambda prime, is a controlled set, and its image is a controlled set.
No, we need proper too.
Yeah, properness will imply that this point is at infinity.
Yeah,
right. So the properness is required to say that f of x lambda belongs to the boundary only since f is proper. Okay, so you need properness for stating this. And that's why the other limit has to be also the same. That is because that the image of E is controlled. Okay, so since this is on the boundary, this implies that f of x lambda prime should be equal to y, as f cross f of E must be controlled. Controlled by y. Right. So this is by hypothesis that f is a large scale map. So first thing is by hypothesis that f is proper, and second thing is the hypothesis of mapping controlled sets to controlled sets. And just because of that, this function is now well defined. I'm somehow getting I'm somehow a little tired in this thing because I confused myself once. So I'm going to skip the continuity still, unless you have a quick way of seeing it. Because I think cannot rely on my memory. Okay. But I can do it again if you like it. But this is the interesting thing. I mean, I like that you guys are still interested in this. This is good news that we have at least one thing. We know how to define the extension. We can define the extension by doing this, but we have to still prove that it's continuous. And the continuity is probably, yeah, I don't want to think about it. I don't remember it. And if I don't remember it, some things can be non-obvious. Although I think it was very obvious when I thought about it. It was very obvious, but yeah, let's just take a break from it. So at least it explains you it's worthwhile to consider compactification, right? This is the whole point of, I think why I don't remember about it is that I prepared it for the last lecture. It's in the notes for the last lecture. And I haven't thought about it since. So I have been thinking about something different now for today. So I will come to that now. Okay, so I apologize for messing this up. But at least you see why this is interesting. It is interesting for extending maps and so on. That's one reason for this being interesting. The other reason is you guys are metric space people. So the other reason is that can we find a compactification? So I will just make the question. Oh, is my thing dying of battery? Can you read this? No. Is there a compactification? So let XD be, let's at least say proper metric space. Is there a compactification? Such that so you have E is controlled by the metric if and only if E is controlled by this particular compactification. Okay, so this is the question that we want to answer, right? So when we have a metric space, we have more than, what are we asking for in this question in another words? What are we asking for in slightly different words? Is that, of course, we have a topological space X. So now I'm reformulating this question. So this is a question of interest. It's a question of interest because then you would say, I would like to study the large scale geometry of the metric space XD, but then I can just study this compactification or its quotients. Okay, so this is why it is an interesting question to metric space, metric geometry people. All right. Now I want to say, think about this a little bit and say, well, you know, how can I reformulate this question? So what is given to me is X is a topological space. So proper means it's locally compact Hausdorff and also paracompact I'm going to add. Right? So this is a proper space is given to me. So it has this topological properties. And the distance has given me a coarse structure. So the distance, the metric that D has given us a coarse structure. So I'm now looking at a proper coarse structure. I'm only looking at the topology and the coarse structure coming from D, and I'm forgetting the D completely. Okay, and then we can start thinking, can we define a compactification given just the topology and a coarse structure? Okay. Oh, I don't want the keyboard to go away. Sorry. So what we would start with is X. All these things together, we will just call a proper coarse structure. So X is a proper coarse space. So implicit in this is that it's a locally compact Hausdorff paracompact space, and it has a coarse structure compatible with it. And this is what I mean when I say X is a proper coarse space. So these two things together is my definition. Okay. Now I want to define a compactification for this. How can we define compactification? What is our recipe? Our recipe is still the same, the functional analytic recipe. We'll define a sub-algebra of the bounded algebras of continuous functions for given with this, which works with this data. Okay. So let me. So now if this is true, then each of these sets E contained in X cross X is locally compact Hausdorff space, right? By definition, because you're taking a subspace of a locally compact Hausdorff space. And I can think of then functions that vanish on infinity at E. So somehow to say that we are including the coarse structure in a compactification, we would like to say the following. So suppose this is the definition. I could not find a more, what you call it, a greater motivation for making this definition. But once you have the definition, other way around is fine. You would always be happy with this definition once you see it, right? So I don't think I need to motivate it that much. So if let X be a coarse space, a function, a bounded, well, it doesn't need to be written bounded explicitly, but let's just write a bounded continuous function f belong to CB of X is called a Hickson function. If the differential of f, can one define a differential for any space? Well, you can define a differential as a function on X cross X. Right, so you can define it as so this is a differential function, if you like. Okay, so the differential function is a function on x cross x, so it's also on every subset of E. So the differential has the property that d of f belongs to C0 of E for all controlled subsets. Right, so if you have any controlled subset, then this should happen. And of course, since we are talking about proper coarse spaces, we can immediately see that any function, any f belong to C0x is Hickson function. So I'm not going to elaborate this, but this is basically saying that our coarse structure is proper. It's proper. Right? We remember we talked when a coarse structure is proper, that corresponds to relative compactness thing, like in the metric space language. This is what we have. Okay. So what do you expect? This is your C-star algebra, right? So this is pretty much the proposition I would make. So Hickson function functions on X for C-star subalgebra of CPX. A unity for a unity. Of course, the constant function 1 is always there because the differential of the constant function is 0. So it's in C0 of anything. Okay, so I'm sometimes making trivial remarks, but this is just to keep you worrying about trivial things. So there is actually nothing. If you add such, differentials get added. Multiply, differentials don't get multiplied, but there is a chain rule. So the proof is basically that there is a chain rule. B f times g x y is basically what you would expect. Bf df x y times gx minus plus fx fy d gx. Simple as that. Okay. So the differentials, if they become C0 and the other thing is bounded, multiplication of bounded and a C0 function is C0. Okay, so this is basically saying product of two Hickson function is Hickson function. All right. So that's our definition. The Hickson compactification of a proper coarse space which is denoted by Hx is the spectrum of the C-star algebra. What about this of Hickson functions? Can you read? No, I haven't written anything. Is there anywhere readable what I write? I now look at it closely. It's all gibberish to me. Oh my God, can you read any of what I write?
Yes.
Wow,
I mean,
you guys.
the thing is, we can listen while you write, so that helps.
Okay. I looked at it with my lens and I couldn't couldn't read whatever. It's just all scribblies. Ah, amazing. Okay, so we have used our background, a little bit of preparation that we did in functional analysis at least one more time. And we have produced to every coarse structure, every proper coarse structure on a nice topological space, a compactification, right? So actually these compactifications are very interesting. You could play around a lot with it. So you can start with different kind of proper coarse structures, and you will always produce a compactification, right? That is the amazing thing. So previously we did what? We are now producing an inverse functor in the language of functors. So we had a functor from the category of compactifications to the category of large-scale geometries. That functor was more or less obvious. We just defined it. We talked about it. But what this process says is that there is somehow an other way around functor too, which is not an inverse, generally speaking. Usually, when you go from a proper coarse space to a compactification, and then you come back and produce the coarse space corresponding to your compactification, you get some bigger coarse space, something that has more control set than what you started with. You end up with more control sets than you started with, okay? When you go through this procedure up and down. But it's still interesting. You can now play a lot with this, and people play endlessly with it. And there are lots of many interesting theorems about that. So, but I'm not going to cover that all literature here. It will take like half a course to just cover that. Okay, but of course, the definition is here. There is a lot of literature available, is what I want to say. And why is this interesting? Of course, why, if there is a lot of literature, there has to be some interest in having this produced, right? What's the point of having this construction? So let me state the basic thing about this. So before I state it, so we have gone from compactification to coarse structure. Right. So what compactifications? So I'm now fixing a coarse structure. So we have fixed a coarse structure on X. In some sense, we are only interested in compactifications that produce a finer coarse structure. That produce a coarse structure. So we want to look at all compactifications. Such that this is not the construction, by the way. This, I will not give you an abstract nonsense version, but the Hickson thing is very explicitly constructed. We just constructed it using the differential. And that's why in many cases you can compute it, right? But this is the philosophy. Sometimes it's good to think about the philosophy as well, although philosophy doesn't help you to compute anything. So we have all compactifications such that if E is controlled in the original coarse structure, then it is controlled by the compactification. So we can look at only those compactifications. So if we fix one coarse structure, we are only interested in those compactifications with the property, with this property. right? Because we have chosen our core structure. So typically this thing will be the one coming from a matrix. So we fix a metric space and its core structure. They start with metric space and its core structure, and you're interested in saying, are there compactifications with this property? Right? So a priori, you would be hard pressed to produce examples of such compactifications. Of course, there is one trivial example, but let's forget about the most trivial examples. Are there such compactifications? And the answer comes from the Hickson compactification that we just proved, is the following answer. So given a proper coarse space X, any controlled set E of the original coarse structure of this is also controlled by Hx. Okay, so this is the first part of it. And second thing is something more, that this is actually universal. And so there is a universal property. So this is A. B is if X bar is a compactification such that any E controlled by the original coarse structure is controlled by X bar, then there is a surjection okay. So this is like, you see such statements also for Stone-Check's compactifications and stuff like that. Okay, so this is more or less how much time we have, by the way. Oh, we have 5-6 minutes, or we have 10 minutes? I cannot read my
6 minutes.
Okay. Good. So I would continue with the tradition of going through this revisions of what we do one time and the next time. So we'll have to do some of the proof next time, because as I've already said, the main goal we are hitting at is, with this statement, you'll get one part of your goal. You'll see that if you start with a proper metric space and construct the Hickson compactification, then everything controlled by your proper metric space is controlled by the Hickson compactification. That will be one half of what you want. And then you need the other half, which says everything controlled by the Hickson compactification is controlled by your proper metric space compactification. So this is inherently, this statement contains one half of our goal that we proposed for today. Okay, good. So see if I have how far we can fix this for in the time we have. So I think this is just I have I'm dropping things. So we begin with just saying that this is true for the Hickson compactification, right? So what we have claimed. So we start with a controlled set E, and we want to say that it's controlled by the Hickson compactification. So we need to then show that, so we have E is a controlled set in the original coarse space, right? And now we have some sequence x lambda, y lambda is some net, it's a net. Okay. And we know one thing, we know that x lambda, say, converges to x in the boundary. Sorry, I should not just say that, in the boundary. Because it goes to infinity. X lambda goes to infinity. But what we already know, what we have assumed about our original coarse structure, that it is a proper coarse structure. Right? So if one thing goes to infinity, the other thing also goes to infinity. Right? So it just basically means if one goes to infinity, oh yeah, I know why I was confused in the proof of the other thing. Now I'm getting, so that means y lambda is also unbounded, or goes to infinity. Okay, but what does that mean? Right, the Hickson functions have the property that they should vanish at infinity. So if both x lambda, y lambda are going to infinity, then x lambda, y lambda as a net is going to infinity in E, right? And that means that the Hickson function, the df of x lambda, y lambda goes to 0, because Hickson function is supposed to vanish at infinity, right? As E is controlled, since E is controlled. And what does that mean? That means that limit of f x lambda equals limit of f y lambda. So for any Hickson function, the limits of these two sequences are equal. So what does that mean? That the sequence gives you a point. So that just means that y lambda goes to the same point. Because if all the function, this is a basic thing in I don't know, a fancy way of saying this is the Stone-Weierstrass theorem. The Stone-Weierstrass theorem says if you have something, continuous functions that do not distinguish points, then the points are the same. All right. So this is basically what we have. So if one goes to infinity, the other will have to go to infinity and have the same limit.
Maybe a little less, a bit more down to earth way to put it is that the space is.
Sorry, what?
Maybe a bit more down to earth is to say that the space is completely regular, right? That's already sufficient.
Yeah, basically, you basically exactly your functions determine the space. The space determines the function. The functions determine the space. So if all the functions have same value at 2 points, then these 2 points have to be the same. Exactly. Yeah, the function is housed of regular. It's a completely regular space. Points have to be distinguished by sort of this Urjon kind of lemmas. Yeah, but Urjon lemma is topology and Stone-Weierstrass is functional analysis. Okay, so we have, how far are we? So we have proved, what have we proved? We have proved that if E is controlled in the original thing, then E is also controlled in the Hickson compactification. So that part we have proved. Okay, so the second thing is if E is controlled by some, if X bar is a compactification with this property, then there is a map from the Hickson compactification to XPAR. So that's the other part. But do we? Okay, we are already out of time. All right, so maybe we have at least done one half of our goal. The other half is not that hard. It's a rather simple statement. And maybe we'll also relate this Hickson compactification, which is a rather simple way of relating to Gromov compactification for in case your space is delta hyperbolic. So we will continue that next time. And I don't know, I'm going to think that we should at least know something about amenability if we have already thought and talked about large-scale geometry. Actually, we can define amenability for spaces, not just for groups. And unfortunately, I don't know applications of amenability for spaces. So that's what we would do. We would define amenability for spaces as a large-scale invariant. And that would be the next thing. So it's not just group theoretic, it will be space theoretic, where the group would be the Cayley graph of the group as a space. Okay. And yeah, that's that maybe for today. Anybody has questions? All right. So Tobias, how do we do? If you record it, then it's not automatically there, no?
Yes, I have to send you the recording, or the other one who recorded too can also send you the recording. Or yeah.
Okay, then I'll see. I can try to put this up. Yeah, I have. Yeah, we are trying to. I'm glad you guys understand my scribbling to some level. I'm very, very worried about making the scribbling available on internet. It doesn't seem like anybody should be able to read anything, because I never read what I write. I've never read anything I've written in the last 20 years. You know what I mean? I write, but I never read. So I never realized on the big board, it's somewhat easier. I also see what I'm writing because it's big then. You know, your letters are as big as your palm, and I can see them.